Okay, good morning, everyone. Let's start. So first, someone asked me for the homework 1, the implementation of the decision trees. Can some like existing implementation be directly used? The answer is no. We have emphasized this point when we talk about the course policy and syllabus, right? So for all the homework assignments regarding the implementation of the requested algorithm, we ask everyone to implement from scratch. You can use some existing numerical libraries like how to compute matrix multiplication, how to call some optimizers. You can do that for sure, but you cannot leverage or use some existing implementation of those algorithms like decision trees, like boosting, all kinds of stuff. The reason is we want to let everyone really understand those algorithm steps, how they work with the real data set, and you need to ensure your own implementation can give some reasonable performance. In other words, it is to ensure that it is working, right? Only for projects like Kaggle computation or exploratory project, you're free to use any off-the-shelf machine learning library. There's no restriction on that. But for the homework assignments, we request everyone to implement by yourself. Okay. So let us continue with the decision tree. A little bit things to wrap up. So now we arrive at topic about the non-Bloom features. Right? So as we discussed before, right, when we run ID3 or any other decision tree learning algorithm, by default, we assume your attributes are discrete. Namely, it can be binary or it can take multiple but finite values. Right? So like outlook feature we used as our example. Outlook can take 3 possible values, like sunny, overcast, rain. Right? And by using this categorical feature to split on a data set, we can imagine that for each particular value, we're going to have a subset. Right? So this seems a natural way, right? It's a multi-way split, but there is some problem in practice, right? What if this categorical attribute contains many possible values? Like one attribute could be brand, right? The brand, you might have 1,000 brands, right? Or like zip code, right? You might have like tens of thousands zip codes, right? Zip code is obviously categorical, but there are so many different zip codes. So in that case, you can imagine when we grow the tree, you're actually growing a lot of branches, right? I mean, in terms of expanding the width of the tree. That actually is be kind of violating our principle to make your tree as small as possible, right? So how can we work around with it? So often use the trick is to make those attributes or convert those attributes to be binary entries. How can we do that? Right? So we can look at each case that outlook takes a particular value, right? So we just test if outlook is sunny, then we got the binary feature, right? So that is, if outlook is sunny, then this binary attribute or feature is true. Otherwise, it's false, right? And similarly, we test another value that outlook can take, like which gives another binary attribute, like outlook is overcast or not. Right? The third one with outlook is rain or not. Right? So you can see that, okay, we originally have like one categorical attribute, which is called outlook. Right? Now we convert it into 3 binary features. Outlook is sunny or not. Outlook is overcast or not. outlook is ring or not, right? So we expand the feature list. However, whenever we pick up a new attribute to split on data set, you can see, okay, this tree at most grow 2 branches, right? Because it's binary feature. Does it make sense? Right? Because we have some like effective and efficient greedy heuristics, we won't necessarily exhaust all those new expanded feature lists, right? So because every time, okay, I pick up one binary attribute, I only grow 2 branches based on the current tree, right? So you're still kind of restricting the tree size. Does it make sense? Right? It's a very popular trick, right? So when you deal with like multi-class attributes or an attribute whose cardinality is large, we usually first convert them into a set of binary features. Any questions so far? Okay. So now let's talk about numerical features. We discussed before, right? We mentioned that decision tree algorithm only apply to discrete features or categorical features. Right? So because for numerical features, those features can take like infinite number of values, right? You cannot create infinite number of branches in your tree. Okay? So how can we deal with them? We're going to use some thresholds or ranges to convert these numerical features into categorical features or discrete features. That's it. So most commonly used one will be, okay, I just look at the range of my numerical features to pick up the threshold in the middle. So now I convert it into a binary feature. Right? If this value is less than the middle value or threshold or bigger than that. Right? And of course, if you want a more refined conversion, right? So you can partition this range into several small ranges. And then you just test if this numerical feature value falls in range 1 or not. If this numerical feature value falls in range 2 or not. And blah, 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 you actually convert it into a set of binary features. It's not necessary. Yeah. Mm-hmm. 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 Yes. Yeah. Yeah. But I think your concern is right, because we kind of like extending the feature list, right? We have more features, but as I just mentioned, because we have some feature selection mechanism, we have some greedy heuristic mechanism, we want to stop the tree growing as early as possible. You incorporate more attributes, kind of increase the risk that you get a taller tree, but it's not always the case. So suppose that you got some like a fantastic greedy strategy that you only select, oh look, it is sunny, and then next will be some raining, some other features like humidity or temperature. You also stop at the same level, then that will bring you additional benefit, right? Because you have the same depth of the tree, but you restrict the width of the tree. But of course, if you increase the list of the features, you got higher risk to have to end up with a taller tree. Right? But imagine that if the categorical feature can take so many values, like thousands of values or even tens of thousands of values, you grow it for one table, you kind of create like thousands or even tens of thousands of branches. That's something definitely you don't want to see. Yeah. Any other question? Okay, great. So those are all the commonly used tricks when you or sometimes we can call it pre-processing. So we want our data set to be clean to be complete. And also I want our attributes or features to be easy to deal with. Okay? So once you have done all this, then you can run the ID3 algorithm. So next, we're going to talk about a very important concept. It's called overfitting. And so you might have heard these words from time to time, right? When people are talking about machine learning, they said, okay, the major bottleneck or nightmare is overfitting, right? But what's the definition of overfitting? Why people are so scared of overfitting? Okay? So we're gonna use decision tree as an example to introduce this concept, and then give a little bit kind of formal definition of overfitting. And actually, we'll see that because the practical data often contains some kind of noises, that's why overfitting is bad. But if your data is noise-free, overfitting is good. So let us consider learning a Bloom function with decision tree as some initial example. Right? So a Bloom function means that, okay, I got like n binary input features or attributes. Like each attribute is either 1 or 0 or true or false. Right? So take this binary feature values, then it simply returns the value of the first feature. That's how I set up this ground truth Bloom function, which is called a first bit function. So if you take a look at this example, right? This is a first bit function where we have two binary attributes, x0 and x1, and the ground truth label is actually the same as the first attribute value, right? So if we manually construct a decision tree or we run our ID3 algorithm, we can easily get this tree, right? Because this first bit function is only determined by the first attribute, right? So if you calculate information gain, it will tell you that the first attribute x0 will give you the largest information gain. Then you're going to use x0 to split on data set. It will give you like 2 leaf nodes, right? So I'll leave it as an exercise for you to convince yourself that ID3 will generate this tree. So this is just one example. If we take a more general view, we'll find that, in fact, decision trees can perfectly learn an arbitrary Bloom function, meaning that, okay, it's not necessarily the first big function, the example we list here, right? For arbitrary Bloom function, which are listed in this giant table, right? And for arbitrary number of Bloom input binary features, we run our decision tree where we're always able to perfectly fit this function. Why? Like imagine you have an n binary features or Bloom features, right? x0 to xn become giant table, right? Why? And this is each row of this table enumerates the possible values x0 to say xn minus 1 can take, right? And then the rightmost column indicates the target function's value, right? Of course, it's still a binary, right? So if you list all possible configurations of x0 to xn minus 1 in total n features, and their function values or target function value, you throw it into an ID3 algorithm, it will guarantee you that the learned decision tree will perfectly fit this training set. Or in other words, if you use your learned decision tree to predict the labels in this giant table, it gives you 100% accuracy. Yeah, exactly. Right. Let me repeat what I said. Okay. So if you look at how decision tree classify each example, right? So it is starting from some root attribute, right? And then go down and second entry testing attribute, third test attribute. So imagine in the worst case, you're gonna exhaust all the n binary attributes, right? Then it must arrive at some leaf node, right? Right? Because once you have exhausted all x0, x1 to xn minus 1, there must be some function value, right? And this is where the decision tree has arrived a leaf node. Does it make sense? Okay. So that's only in the worst case, meaning that you grow the tree to be n levels, right? You use up all the attributes. But once you use up all the attributes, meaning that you test every value, the value of every attribute can take, right? And that then at that stage, you must know the function value, right? Because the target function is defined only on this n attribute values. Not to mention the case that, okay, if this function is very easy, meaning that a bunch of different settings of x0 to xn end up with the same function value, well, you don't need to use up all the attributes to get the leaf node, right? You might just use 4 or 3 to get to that leaf node, right? Like this first bit function, you only look at x0, you know the function value, right? But if it is not, you at most test x0 and you at most test x0 and x1, then you must know the function value, right? Any question? Is everyone comfortable at this conclusion? Right. So yeah, just if you still feel like uncomfortable, sit down after class. Sit down for 5 minutes. Think about how decision tree classify each example. Okay. So you can imagine the decision tree starting from some root node and find out the path goes through every possible feature value. You will end up with some function value. Why? Because the target function, the balloon function itself, is solely dependent on this n feature values. Right? Once you know there are feature values, you must know the function value. There won't be any confusion. So yeah. So if you still feel uncomfortable, just I mean, after class, see for 5 or 10 minutes to think about that. It's relatively intuitive, right? So now, based on this observation, like given this n attributes, right? Suppose we have all 2 to the power of n examples for training, meaning that we enumerate all possible instances in the instance space, right? So remember, n balloon features correspond to n-dimensional input space, and each feature takes 2 possible values. Then the total number of possible instances in the whole instance space will be 2 to the power of n, right? So now, if we use all those examples for training, now with the trained classifier or decision tree, what will be the error on any future examples? I heard that, right? 0, right? Because in the training stage, we have already seen all possible instances in instance space, right? If you use some future example to test, it must, because decision tree has already seen 8 in the training stage, and the decision tree is known to perfectly fit all the training data set, right? So it will correctly classify that future example as well. So in that case, we're gonna have like a 0 testing error. Right? Everyone is good? Okay. And the decision tree can represent the function, and this tree will build consistently. This just explain why the error will be 0. Okay, based on this conclusion, now let us consider a little bit practical influence. So we know that in practice, things won't be that easier. Like you have collected all the training instances all the possible instances in the instance space for training, and test example will just belong to the trained data set. Well, in that case, it's perfect. In the ideal case, you give 0 test error. But what if the data is noisy? Right? And let us assume we still have these 2 to the power of n examples for training. Right? However, due to some random noise, right, the outputs of both training and test sets are corrupted randomly. Okay? That is very possible. Right? So imagine that when you collect some data from the internet, those data might be corrupted. And even when you label some data set, you have some like destructive things. You might get a wrong label. Right? This is very possible. Right? And once the data set is corrupted by some noise, we know that the train and test sets are no longer identical. Right? Here we just talk about the corruption in terms of labels. Right? We just both have noise and possible different. Right? So we just make the case a little bit simple to understand the idea of this overfitting. Right? So assume that, okay, in some training set, maybe this second example, the original label should be false, but now it is randomly flipped to choose. And this third last example, the label is randomly switched to false, right? Similar kind of corruption applied to the test data as well. So now, let us assume the chance that we corrupt the training output and test output for every example is 0.25, meaning that for every training example or every test example, the output has a chance of 0.25 to be flipped. Right? So now we still use this corrupted training set to run ID3 to train our decision tree classifier, and then test our learned decision tree on those test examples. Right? So both test and the training sets contain the 2 to the power of n examples, meaning that both training and test instances cover the whole instance space. Right? Then what will be the error? So first I want to ask, will the test error be 0 still? No, right? Why? Because the test labels or training labels are randomly corrupted, right? They're not guaranteed to be consistent. So you can well fit the training data set, but when you test the same example, right, with different label, then of course your prediction will be wrong. Right? So if we do some like experiments, manual experiments, right? So this figure shows how the test error varies along the number of input features you use. Right? So you can see that when we increase the number of features from 2, 3, 4, 5 until like 15, you can imagine like when you increase the number of features, meaning n, right? The instance space is getting larger and larger, right? So you got more and more stable estimate of the test error, right? Test accuracy. So and we can see that, and also these bars are just the standard error bars. Right? You run it many times, you get the mean and standard deviation. Right? So you can see that when you increase the number of features, the test error kind of like converge to approximate 37.5%. Right? This is some like you do experiments, you see that. But actually, we also can get this error by mathematical analysis. Right? How can we do that? So let us just calculate some probabilities. So we can calculate the correct prediction for an arbitrary test example in this way. Right? So when the training example, when a particular example will be correctly predict at the testing stage. Two possible cases, right? One is that, okay, in the training stage, this test example is not corrupted, meaning that, okay, it maintains the original label. And also, in the test stage, the label is not corrupted as well. So meaning both this example at both the training stage and test stage, they keep the original label, right? Because our decision tree classifier will always fit the training example, right? So if the test stage, the label is the same as that label in the training stage, of course, it's gonna make a correct prediction, right? That's just one case. Another case will be in both stages, the labels are flipped. Right? For this label, for this example, okay, the ground truth label might be truth, right? But if in both the training stage and test stage, they flipped to false, then that's fine, right? Because it still guarantees that the label at test stage is the same as the label at training stage, and then you're gonna give correct prediction. Right? So we just calculate the probabilities that is two cases, and then we add them together. Right? So the probability that the training example is uncorrupted is 0.75, right? As we mentioned, the probability of corruption is 0.25, so it's uncorrupted, of course, is 0.75, right? And also the probability that test example is uncorrupted is 0.75. Here we assume the corruption of each example happens independently, right? They do not relate to each other. So we got the probability of the first case to be 0.75 times 0.75. And the second case is that, okay, in both stages, this example is corrupted, right? And the chance is 0.25 times 0.25. Right? Now you just add them together, you end up with the probability you make a correct prediction is 0.625. Right? And then the error of the probabilities is 1 subtracted by 0.625, which is 0.7375. Does it make sense? This is consistent with our experiments. And similarly, you can directly analyze the probability that you make incorrect prediction. Right? That's fairly straightforward. It's very similar to here, right? When we look at one particular example at test stage, we have two cases that test example will be misclassified. One example is that, okay, this example at the training stage is uncorrupted, meaning that the label is the original label. However, at the test stage, it is corrupted. The label is flipped. And of course, the classifier will make wrong prediction. Okay. And the chance will be, okay, uncorrupted at training stage is 0.75, and corrupted at test stage is 0.25. You just multiply it. Yeah. We assume that if they are corrupted or not corrupted, these events are independent of each other. That's why we can multiply them. So far, let us assume the training set and test examples are independent and drawing some unknown data distribution. But of course, if you want to make the association between them, that's some kind of research topic. And another case will be, okay, at the training stage, the label is corrupted. Well, at the test stage, the label is uncorrupted. Right? So the probability is 0.25 times 0.75. If you add them together, it gives you the probability of incorrect prediction is 0.375, right? Which is the same as the experiments reflect. So any questions so far about this analysis? Yeah, of course. We don't assume those examples are duplicated. Yeah, regarding the duplication, we'll talk about that when we talk about random forest. We'll talk about ensemble learning. Yeah, we kind of review those examples. We have duplicated these examples where decision trees can easily deal with them. But as for now, let's just assume, okay, these examples are drawn independently. They're not. There's no duplication among them. Explain what? Okay. This just to increase the x-axis is the number of features, right? So for every particular choice of number of features, you just use 2 to the power of n examples for training, 2 to the power of n examples for testing. But before that, of course, you need to conduct some random corruption procedure, where for each training example, the label has the probability to be corrupted 0.25. So does it for corrupting test examples. So once you collect those examples, just train them and test on the same set of examples, but with probably a different set of labels because they are corrupted. And then you look at the test accuracy and the standard deviation. And you can see that because we increase the number of features, the data size is getting larger and larger, right? So you can imagine the test accuracy will become more and more stable. If you only have 10 examples, of course, you test this time and test next time might be different. Right? But if you have like 2 to the power of 16 or 15 examples, many, well, the test error won't change much. That's why you see the standard deviation is getting smaller and smaller. The probability just tells you, okay, if you pick up any test example, the chance it gets is 0.375. This is the probability. And in practice, you can imagine, okay, I want to see the chance, right? I want to see the chance like you toss a coin. Like you know the chance, you know the coin has 0.5 chance to show heads or tails, right? But that doesn't necessarily mean that you draw a coin, you will end up with you can only end up with tails or heads, right? If you run it 10 times, you might see 6 heads and 4 tails, right? The ratio is still like 0.6, it's not 0.5. If you want to make it close to the theoretical value, you have to run a lot of experiments and then look at the ratio, right? That's the difference between the experiments and the theoretical analysis. Yeah. Any other question? Okay, so now we see that, okay, by just some random corruption of those labels, you can see the huge difference in the test accuracy, right? But what about the training accuracy? I heard that training accuracy is still 100%, right? Accuracy. As we just analyzed, right? Whatever Bloom function, your decision tree can perfectly fit that Bloom function, right? Even you corrupt some labels, change some labels, doesn't matter because it's still another Bloom function. So for the training accuracy, it always give you 100% accuracy. Okay? Because the learning algorithm will find a tree that agrees with the data perfectly. However, because the random corruption and the discrepancy between the training labels and test labels, now your test accuracy drops dramatically. Right? So the question is, why is the classifier now perfect? Because the classifier overfits the training data. No matter your data is ideal or contains some noises, the classifier will always perfectly fit the training data. In other words, it gives like 100% accuracy in training data set. And when data contains noises, those noises can mislead your learning of classifiers. And harm your test accuracy. Right? That's why we don't like overfitting. Right? So what does overfitting mean? Right? Overfitting means that the learning algorithm fits noise in data. Like for example, the irrelevant attributes or noisy examples influence the choice of the tree. Then, as a consequence, no matter what kind of noises are in the training set, your algorithm always fits the noise in the data to get very high training accuracy. And those noises kind of mislead the classifiers and mislead the tree construction. Then finally, we'll end up with the bad accuracy in testing the future on same examples. That's the bad effect of overfitting. So if the data doesn't contain any noise, then overfitting is good, right? Because you're trying to fit all the right labels. However, if the data unfortunately is corrupted by some noises, then overfitting is bad because those noises can lead the learning into some wrong ways, right? And then when you use this learned classifier, although it has like nearly 100% accuracy in fitting the training set, it gives you a much worse test accuracy. Any questions so far? You want some concrete example of showing? Oh, that's a good. We're gonna reach to that point. Like, if you have like a set of training examples which are large enough, and let us assume we don't have any noises, we will show some error bound and say that okay, we will increase the number of training examples, and assume you can overfit that data that doesn't contain noise. The generalization accuracy will be better and better. But here, that will be when we talk about the computation learning theory in the next stage. But here we want to first emphasize the practical point of view why overfitting is not favored. Right? So again, it's not because the algorithm issue, it's because the data issue. Because the data itself contains noises, which is often the case in practice. And if your algorithm is so strong, you kind of like overfit the noises to account for the noises to get like very high training accuracy, then that will lead some problems. You have a question? Yeah. Yeah, that's a very good question. But the analysis for non-Bloom features and non-Bloom labels will be much more complicated. And here we just want to use this simple mathematical model to showcase how overfitting is harmful when the data contains noises. But if we want to say, okay, in practice, suppose we're dealing with non-Bloom features and like multi-class classifications, how overfitting will hurt the performance. We're going to look at this example. Usually we won't do that. Usually the strategy to handle the overfitting, as we will discuss in a minute, is to control the model complexity. Meaning that I don't want my model to gain 100% training accuracy. I want it to be give like only 80% training accuracy or 85% training accuracy. Then I stop the tree growing. In that case, you can view like, okay, the noises cannot manipulate the training so much. Right? We still assume, okay, most of the information in the training data set is still correct, right? Not corrupted. So if you can give like reasonable, good training accuracy, we should stop. We shouldn't seek for like 100% training accuracy. And this is the most effective way to alleviate overfitting. But as to the strategy you just mentioned, like adding some noises, I think it will be useful in some cases where when your training set actually is not noisy, but you expect your test set is noisy. In that case, your performance might have the chance to degrade. So in that case, you might just intentionally add some noises in the training set and then employ some overfitting control strategies as we just discussed, and then to increase the generalization capability. Another question before we proceed to some more practical investigation of overfitting phenomenon. Okay, good. So now, as we just mentioned, like the binary features and Bloom functions, this is a very simple case, which might not match the majority of the practical applications, right? So in the practical applications, how can we see the overfitting's influence, right? So here we list one figure. So this is a figure drawn from Tom Michel's classical book about machine learning. So the x-axis is the size of tree. So basically it calculates the size of tree in terms of number of nodes, right? So you can imagine like the larger number of nodes, the more complex the tree is. It is, but at the same time, you can imagine the larger the tree, it can better fit the training data. So you can imagine larger trees will give you a larger training accuracy, right? So the y-axis is accuracy, and we got two lines. One dashed line is the training accuracy, and the solid line is the training accuracy, and the dashed line is the test accuracy, meaning that we have sampled a large set of test examples. So you test the accuracy on those test data, and those test examples are now saying in the training stage. And this is from some practical data set, so which you can assume there must contain some noises there. So we can look at when you grow the tree, you make the tree bigger and bigger, how the training accuracy and test accuracy vary. Right? So first, with increase of the tree, right, the training accuracy keeps increasing, right? Meaning that it can better and better fit the training data. But what if the test accuracy? Right? What can we observe about test accuracy? Yeah. We can see there is some like a turning point, right? So at the first stage, before that turning point, which is when the tree size is around 20, right? Only 20 nodes. So we can see that when the tree size is below 20, we will increase the tree size, the test accuracy, which reflects the generalization performance, keep increasing as well, right? But after the size of tree beyond some threshold like 20, the test accuracy actually kind of decreasing, right? It's getting worse and worse. So this is the typical phenomenon of overfitting. So basically, before this threshold 20, right, size threshold 20, when you make your tree larger and larger, you increase both the training accuracy and test accuracy, meaning that, okay, you're increasing your model expressivity to be better and better classify new examples. However, after this particular size, we'll still increase the model complexity. You kind of like overfit the training data, especially misled by the noises or errors in the data. And as a consequence, your test accuracy on those future unseen examples starts to drop. So in practice, no matter, I mean, decision tree is just one example to showcase that. You'll see this phenomenon very, very frequently, especially if you use artificial neural nets, the so-called deep neural nets. And people often draw some figures like this. Right? So just to look at on some validation data set, when this turning point appears, they just stop at this turning point. They won't continue the training. Okay, so now we know, okay, what is overfitting, right? Why overfitting is harmful in practice. The natural question is how to avoid overfitting with decision trees. Right? So, of course, we cannot make the tree to grow too large, right? Too wide, to grow arbitrarily. And if you allow the tree to grow arbitrarily, it's very likely that you will get very high accuracy, but bad test accuracy. Right? So then, how do we control the tree size? Okay. So an immediate idea will be we just fix the depth of tree. For example, I just require that my tree cannot exceed like 3 levels. I just set up a maximum depth of tree. How can we do that? How can we do that in the ID3 algorithm? Yeah, that's one way, right? But when we talk about how to fix depth of tree, you just record the tree depth for every node, right? And if the tree depth has already arrived the maximum depth, you just stop calling itself to grow the tree anymore. Right? You just add one if-else condition in your ID3 algorithm implementation. And there's some extreme case. What if I just allow my decision tree to grow one level, meaning that I only select one attribute to split on data set, and then I stop. Right? And this decision tree is called decision stump. It's a very, very simple decision tree. Of course, this is not to avoid overfitting. It's actually underfitting, right? Because the tree is so simple. But this tree turns out to be very, very useful. And when we talk about boosting algorithm, we'll ask you guys to use decision stump to implement ADA boost algorithm. Another more refined approach is to introduce the so-called held out set, meaning that, okay, I just random pick up like 100 examples out of my training set as my additional held out data set, right? Or sometimes people call it validation set or development set. And then when we grow the tree, every time I just test if on the held out set, my performance, my accuracy will increase or not. If it doesn't increase, then we just stop the growing or cancel the growing. Okay? We just do this test on every splitting stage and to control the tree size. That's another way, but it's a little bit tedious, and the implementation is not that convenient. And the third approach is to first grow the full tree to be as large as possible, right? As deep as possible. Then we introduce some post-pruning process. Right? We can prune that, either use a validation set from bottom to up greatly. Right? So from leaf nodes to top nodes, or we just convert the tree into a set of rules. Remember, the tree is essentially a set of rules. Right? We just enumerate all the passes from the root to every leaf node, and then just look at which rule we are able to prune. Right? So those are 3 commonly used strategies to control the tree size and to avoid overfitting or to alleviate overfitting. And in practice, the most convenient or most often used way is to just fix the depth. Right? Maybe you can just tune the depth of tree on some validation data set, and then determine, okay, the tree depth to be 6 or to be 5 will be the best tree depth. And then I rerun the algorithm to recreate the tree with that maximum depth. Okay. Okay, any questions so far? Oh, decision stump is that, okay, I'm gonna only use one attribute. I select one attribute, for example, who gives the largest information gain. Then I, according to that attribute, I split data set into several subsets, right? For each subset, I'm gonna assign a leaf node. I use the majority label in that subset as a label for that leaf node. That's it. So only in one level, right? So of course, this tree is not to overfit data. It's actually underfit data. It's not powerful. But you will see that it will be useful to construct a boosting algorithm, because boosting algorithm is based on like the so-called weak classifiers. Right? Yes. Yeah. 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 Yeah, that's a good question. That's involves a lot of details. You have many choices. That's why I'm not planning to talk about that in very detail. But you only need to know that, okay, we have this kind of strategies. But of course, how do we discard one whole rule or just truncate that rule? It's up to the particular application and the user choice. You have a tree, right? And it just depends the depth, how many levels you're gonna grow the tree, right? So if you first use attribute 1 and the second use attribute 2, you got level 2, right? And based upon attribute 2, you use attribute 3, it's level 3. Right? It's just a definition. Other question before we summarize about decision tree? Okay, so now we have finished the discussion of decision trees and introduce a very important concept called overfitting. We're gonna revisit this concept from time to time. Okay. So to summarize, decision tree is a popular machine learning tool. The prediction is really easy. It's very expressive. Imagine, recall the decision boundaries, right? So even for several like continuous features, when you thresholding them into binary features, if you look at the decision boundary, it is actually quite nonlinear. So you see that why decision trees are so expressive when we talk about linear models and linear classifiers. You see a linear classifiers, their decision boundary is always a line or a plane or hyperplane. It's actually less expressive than decision trees. Right? And the learning itself is essentially a greedy heuristics, the ID3 algorithm. And we talk about why we use this greedy heuristics. The goal essentially is to be consistent with the so-called Occam's razors principle. Right? We want to make the tree to be as small as possible, but globally, finding a global minimum size of the tree is NP hard. It's so difficult for the computational perspectives. As a trade-off, we use this greedy heuristics. The idea is that, okay, we don't do the backtrack. Every time we just look at the current stage, which attribute can give you the maximum improvement of the label purity. So expect that only after a few steps of pruning, all the tree leaves are uniquely labeled. So we overall we'll end up with an overall small tree. That's the idea of ID3. And this decision trees can be extended to regression case as well, we discussed before. And decision trees are prone to overfitting. Right? Consider the balloon function learning case. Right? If you don't restrict the tree size and let it grow arbitrarily large, arbitrarily wide, it can give you zero training error. Right? Of course, in practical cases, especially when the noises are so common, we do not favor this to happen. That's why we should use some tree growth control strategy to avoid overfitting. Okay. So now we're gonna talk about topic. So now I talk about a brief introduction of the computation learning theory. So don't worry, we'll just introduce several fundamental concepts about that. We don't want you to be stuck in like numerous mathematical derivations and proof. This is not the goal of our work, of our class. So our course emphasizes more on practice. However, to understand some important algorithms and understand why machine learning works and what is the mechanism underlying machine learning, it is really, really important to understand several concepts. And you will use that concept to learn some well-known classical algorithms like support vector machines. You see that support vector machines are stimulated or motivated by the computation learning theory, the so-called generalization error bound. Right? But again, we won't spend too much time on introducing computational learning theory. We won't ask you guys to give many proofs. We will give some like analysis, and which is based on some basic probability inequalities and also definition of the probabilities as we reviewed before. But other than that, we won't go further. If you are really interested in the theoretical perspective of the machine learning, there's some link to the resources in our course website. There's one, I think there's one CMU course is the whole semester is talking about the computational learning theory. So if you're interested, you can take a look at that. But here we only introduce several important concepts. Okay, so we're going to give a general framework about computational learning theory. You see that why should we build up such a framework to describe the capability of learning algorithm, and also to define what's the meaning of the learnability. So we're going to introduce two fundamental concepts. One is called the empirical error. The other is called the generalization error. And then with these two errors, we're going to state the goal of the computational learning theory. Then we'll define a very important concept called pack learnability. Right? So about 10 years ago, the inventor of this pack learnability was awarded the Pruning Award, a Nobel Prize of in computer science. It's kind of a counterpart to the Nobel Prize in computer science. Right? So you can see how insightful, how impactful of this pack learnability definition. Right? And then we'll throw some like ideal and simple example to make formal connections to the principle of Occam's razor. In other words, we want to give some kind of justification of Occam's razor in terms of sample complexity using the computational learning framework we introduced. Okay. So before we proceed, here's the checkpoint. We look at the bigger picture. We have gone so far, right? So we have introduced the framework of supervised learning, which consists of instances space, label space, and the hypothesis space. Hypothesis space is actually the range of functions over which our learning algorithm search over and find out a function close to the target function, right? So we want to prepare a set of labeled training examples and feed them to our learning algorithm, right? Our learning algorithm will generate or find out a learned hypothesis, small h, right? And this is our learning result. We hope that h is very close to the target function. And then we can use h to make prediction for future unseen examples. Right? This is a supervised learning protocol. And under this supervised learning framework, there are a variety of learning algorithms like decision trees, perceptron, least mean square, support vector machines, neural networks, which we're going to discuss one by one throughout this semester. But we have just finished the introduction of decision trees. And also we have talked about the general machine learning ideas like overfitting. Right? That's really, really important. So far, any question? Yeah, we're on the same page, right? Okay. So now let us talk about computational learning theory. Right? So here's the basic setting. Right? We suppose we have a machine learning model, right? It could be decision tree, it could be a linear regression model, it could be artificial neural networks, it could be perceptron, etc. Right? and we train the model on some fixed finite training set. Then we want to deploy this model in a while, okay? And to predict a variety of unseen future examples. Then the natural question is, how well will our learned model perform on the future instances? So you see that the computational learning theory tries to give some theoretical estimate of this. This is the goal of computational learning theory. And of course, if you want to get this performance, we call it generalization performance, you got two ways, right? One way is that, okay, I just collect as many test examples as possible. I test on my learned hypothesis, and then I look at error, right? That's like how we do this in practice. From theoretical perspective, we want to estimate this. I want to derive some bound on that. And based upon how well your learned classifier fits the training set, like suppose I got training error or training error to be 0.05, right? So I want to bound my generalization error on all possible future unseen examples. See if I could claim that, okay, given my training error 0.05, I can bound that my test error won't exceed 0.09. That will be the goal of computational learning theory. But later we'll see that to bounding such kind of error is really, really difficult. And we can now say, okay, we can derive some deterministic bound. And this bound has to be put in some probabilistic sense. Okay, so let us first to introduce those basic concepts. Let us first give out a set of notations for supervised learning, right? So we use big X to represent instance space, right? So namely, the set of all possible examples in tests and training, right? And by the way, the instance space X can be infinite, okay? So for the balloon attributes, well, the instance space is finite because 2 to the power of n, right? However, for numerical features, right, every feature can take infinite number of values, right? So the instance space can contain infinite number of instances. So just to be aware of that. And then we introduce the notation C to define the so-called concept space. So what does it mean for concept space? It just means the type or the family of the target function we want to learn from data. For example, if my target function is a polynomial function, then my concept C is just a polynomial family of functions. Right? It's just type of functions. If my function is exponential, my target function is an exponential function, then my concept space C, it just indicates the exponential family of all functions. So you can imagine your target function is one member in your concept space. Okay. And then hypothesis space. Hypothesis space is also a set of functions, but here is the set of possible hypotheses or functions from which our learning algorithm will search over. Okay? In other words, we're going to search among the hypothesis space to find out a best function as our learned result. Right? We believe our learned result, which is picked up from the hypothesis space, is close to the target function. Sometimes, if you assume your hypothesis space is so large, it even contains the concept space, then you might expect that, okay, my learning algorithm can directly identify the target function because it's also in the hypothesis space. Okay. And the training instances. Right? Training instances are a set of input examples, which we denote by S, and multiplied with this label space -1 and 1. Okay, so this is just assume, okay, we have binary labels -1 and 1, right? It can be replaced by multi-class labels or even numerical labels for the regression test. And then after we are giving instance space X, we're giving concept space C, hypothesis space H, and also training instances. we want our learning algorithm to find out a particular hypothesis, small h, from the hypothesis space, such that the prediction made by our learned hypothesis is consistent with the prediction made by the target function or the ground truth function. Okay. So here we got two cases, right? One is that, okay, I want for every instance in the training data set, the prediction made by our learned hypothesis is the same as prediction made by the target function. And second case is that, okay, we want for every instance in the instance space, the prediction is the same as the ground truth. Okay. So which one would we like to pursue? Yeah, the second one, right? Of course, it's our ultimate goal, right? We not only want our learned hypothesis to well fit the training data, right? But also perform well in the test stage, meaning that for every possible cases in test hypothesis in the whole instance space, we make correct predictions. But you will see that this is actually very, very hard. So here we want to introduce a basic setting, meaning that we assume the training instances are generated by some underlying data distribution. In other words, the training data collection is kind of random procedure. This is reasonable, right? Like when you collect a bunch of training examples, even you collect from the web data set, right? You collect them from Google Image or Google Doc or Google News. This time and next time you get a collection of different examples, right? So result of loss of generality, we assume that there is some underlying distribution which drive the generation of those instances. In other words, we assume some probabilities distribution over the instance space. Right? Some kind of examples are more likely to be generated. The other type of examples are less likely to be generated, right? And then under taking into this unknown data distribution into account, right? We expect that we learn a hypothesis H. We evaluate H on subsequent new examples, which also join according to this unknown data distribution. In other words, the training and test data are both generated by same underlying data distribution. But here I want to emphasize, this data distribution is really very, very hard to get a closed form. And you can only assume, okay, there's some kind of random mechanism to generate those data, right? But you usually don't know what the distribution is. It's not normal, it's not student T, it's not Cauchy distribution, it's not, it might not have any analytical form. It's very common. Okay. So any questions so far about these settings? Because these settings are very, very important for us to proceed to the next definition. Okay. So now, given this data distribution D, we can now define the so-called generalization error. So previously, we always say, okay, what is generalization error? Meaning that, okay, if I can pick up an example out of the training set and I make a prediction, I say the error is a generalization error. But what is the formal definition? What is some rigorous definition, right? Given a distribution D over the instance space or examples, right? We define the generalization error of a hypothesis H with respect to some target concept or target function F as follows. So basically, it's defined as if you randomly sample an instance following this data distribution D, what is the probability you'll make a wrong prediction with your hypothesis H? That's it. So basically, it's just a probability that you make a wrong prediction. And the test example generated follow this on the line data distribution D. So that's the definition of the generalization error. So any question about this definition? X is sampled from distribution D. It's a we usually use such kind of notation to denote, okay, for some example generated by some distribution. Is everyone comfortable? Okay, great. So now I want to give a more intuitive illustration of this definition, right? So suppose this is our instance space X, right? So as we mentioned, we assume, okay, both training and testing data are generated from some data distribution D. That means, okay, we have some data distribution D over the whole instance space. And if you look at the target function or target concept F, and if you use F to label all the examples in the instance space, so this ellipsis, the blue parts shows all the positive labels, right? And outside of this ellipses are labeled as negative. This is where the ground truth label are distributed, right? And if we learn hypothesis H, right, so we can use H to make predictions on the instances in the whole instance space, right? Of course, there could be some discrepancy with the ground truth, right? So suppose this is where our hypothesis space H make positive predictions, right? And of course, outside of this second ellipsis are all the negative examples labeled by our hypothesis. So now where does the error come from? The non-overlapping part, right? So if we look at this part and this part are where F and H disagree. Then the generalization error is defined as actually the probability here over these two parts. Okay. That's the generalization error. Any questions so far? Okay. So this is a generalization error. And remember, generalization error is always our ultimate goal. We want to minimize our generalization error. Right? However, in practice, because it is always difficult to get this unknown data distribution D, so it's really infeasible to compute the generalization error. We can only estimate them. Right? So another common used error in machine learning development is called empirical error. So what's the definition of empirical error? I don't want to read this lengthy definition, but I can tell you empirical error is just training error. So basically, you apply your hypothesis H to predict every example in the training set. You just look at the ratio of the mispredicted examples in the training set, which is the empirical error. Okay? So we denote empirical error by error S H. Why? Because S is the training set. So now based on, oh, by the way, any question regarding the definition of empirical error? It's straightforward, right? Okay, so now based on empirical error and the training error, generalization error, we can define overfitting more formally. So what does overfitting mean? It means that when your empirical error on the training set is substantially lower than the generalization error. When this happens, we can say, okay, our learner or our learning algorithm kind of overfit the data. Right? Why? Because you got so low, so small training error or empirical error, yet your generalization error is large. Any question? There's no restriction about the number of examples to compute the empirical error. So as long as you have collected the training set, you run your learning algorithm to get a hypothesis, right? you use your hypothesis back to test the training error. This is your empirical error. That's regards the how you evaluate that, how you want to estimate the generation error. But here, when we talk about the generation itself, imagine that given a hypothesis H, when it's fixed, then this ellipsis or this circle is fixed. Right? You know, although you cannot compute, but you know there exists some non-overlapping part here and here, which indicates their error. Right? But later we'll talk about actually empirical error is kind of a statistical estimate of the generalization error. Right? But of course, the larger number of examples in your training set, the better estimate of such error. Right? And it was and you based on that fact will derive that the larger number of the training examples will lead to smaller generalization error. Right? That's all about those all will be talked about in the next lecture on Thursday. Okay, let's stop here. See you on Thursday.
So, how many times of the decision to